So first thing, in any mechanics course, whether it's aerodynamics, fluid mechanics, solid mechanics, you have two parts in a mechanics course. You have the kinematics, that is the description of the motion itself, and then you have the dynamics. And without understanding the kinematics, you can't understand the dynamics. And the dynamics in our case is this lift, the lift generation, the moment generation by the wings and so on. So we were starting to talk about wind speed and ground speed because these are the two more important parameters. So let's talk about the ground speed, and which we will refer to as VG. So V ground. This is the this is the speed that you see on your monitor when you're in a flight. And here in this case, it's 294 miles per hour. And the way that you compute it is just the distance traveled over time. So over time. So if this path is 1,000 kilometers, it took you 1,000 minutes. That means your speed was 1 kilometer per minute, and you get the idea. So that's the ground speed, and it's the speed that of the airplane that an observer on the ground, sitting on the ground, sees, a fixed observer on the ground. Then you have the atmospheric air speed, the atmospheric air that surrounds this airplane. So this airplane will have air around it because it's sitting in air, and we're particularly interested in the air within tens of meters of this airplane, and it's measured by this radar station, and that's the pilot will tell you at takeoff that within 2 hours we're going to face turbulence and so on, and they would know this because there's a ground station that can penetrate to hundreds of kilometers and tell you what the weather conditions or the expected weather conditions. So this is a crude measurement. It doesn't tell you exactly, it doesn't tell you the exact speed, but it's necessary. Just because the airplane is suspended in the air, you really need to know what the wind speed that's surrounding in the atmosphere is, the atmospheric speed is. And then you have this ground speed, and the difference between them is what we really worry about in fluid mechanics, and that is the relative velocity. So that's the velocity for someone sitting on the airplane. They will see the wind coming at, and you cannot measure it with the GPS just because the atmospheric wind speed reading that the radar station has provided you with is pretty much inaccurate, and we will come to that. We will come to that in a minute. So the relative wind speed is the speed that someone sitting on the airplane sees coming toward the airplane, and it's measured by a device called a pitot tube. So you'll see on this particular model, there's a pitot tube right here. On the other model, you have two pitot tubes right over there. And if you zoom what the pitot tube is, it's a little pipe. It is hollow on the inside. It has two conduits in the inside, as you might remember from MECH 314. So please go to your MECH 314 fluid mechanics lectures, because we solved this problem or a similar problem. And this thing sticks out around 5 to 10 centimeters from the body of the airplane so that it's not affected by the body itself, by the boundary layer on the body. And as the air enters the little tiny opening at the port, it induces an increase in pressure, and that increase in pressure is translated into a velocity. So this pitot tube measures our relative velocity. And from now on, all the velocities that we are going to be using in our aerodynamic calculations is this relative wind speed. So it's the speed seen by an observer sitting on the airplane. So it's used in all our aerodynamic calculations. So we're going to drop the R because we know, so from now on it's the relative, we know it's relative. And it's this one that we have used in our lift generation forces, lift generation of the lift force generation. And sometimes we write it as V infinity or U infinity or just V. So they mean all the same thing. It is the wind speed, the undisturbed wind speed seen by someone sitting on the airplane. And undisturbed means it's not disturbed by the presence of the airplane, it's not disturbed by the boundary layer, and so on. So why? When we go back here, we said it's not. You cannot get the relative wind velocity from subtracting those two, because you can measure this with the GPS, the ground speed. You can measure the atmospheric speed from the radar station. And why don't you do the subtraction? Because it's not accurate. And let me tell you what that does if it's inaccurate. If you have, because looking at this formula, the more important formula in fluid mechanics in making an airplane fly, or in aerodynamics in making an airplane fly, let's say you have a 10% uncertainty in measuring the V infinity. So when you have 10%, 1.1 times 1.1, that's 1.2. So you're going to get a 20% uncertainty in lift. What if you have a 20% uncertainty in the V infinity? Then that means you're going to get a 40% uncertainty or error in the lift, and that is too much to handle. Only 20%. So you really need this to be very accurate, and you really need it to be sitting to give you the reading second by second as you are flying through all these atmospheric variations, because the atmosphere varies quite a bit in a very short period or in a very short distance. But why is the relative velocity the important velocity in aerodynamics? Primarily because all the mass fluxes and momentum fluxes are based on the relative velocity. Imagine that you're sitting on the beach, you have a pile of sand, and you're trying to scoop this pile of sand. Imagine the pile of sand, so now you're scooping, right? And that's your pile of sand, and this is your scoop. Imagine now that your pile of sand is running from you at the same speed that you're coming at. How much sand are you going to scoop? You're going to scoop none. You're going to scoop zero sand, mass of sand. You're not going to get anything. So the mass flux is zero because it depends on the relative velocity. But now imagine that the pile of sand is stationary and you're scooping. You can scoop as much mass as the amount of mass that's commensurate with the velocity and area that you're talking about. So mass flux, that mass that you scoop, also contains in it energy and also contains in it momentum. So momentum fluxes translate into force balance, and energy fluxes translate into energy conservation. So here is the slide from your MECH 314, and you can see that the mass flow rate is really based on the relative velocity between the area you're looking at, how much mass going through that particular area, the perpendicular relative velocity to that particular area. And the same thing, if you look at the force balance, Newton's second law for fluid mechanics, for a control volume in fluid mechanics, you'll also see that all the momentum fluxes have a V relative in it. So without knowing the relative velocity, it's very hard to compute to get an accurate force balance. So that pitot tube reading feeds into the computer of the aircraft, and it feeds into the generation of lift forces and adjustment based on what the weather conditions are and what that V relative is. We talked about, so now what are the implications of this relative velocity? Last time we talked about this mental exercise that you take a helicopter, you climb up, stay there for an hour in the atmosphere in the absence of wind. Because of the rotation of the Earth, are you going to land in a different location? Because this would be a great, in fact, this would be a great mode of travel if you can just do that. And the answer for a helicopter, as we know it today, that doesn't work because you are actually sitting. The force that lifts you, up in the atmosphere is generated by the rotary wings, the blades of the helicopter, and those rotary wings are creating an action on the air, atmospheric air, and that atmospheric air is lifting them up. But that atmospheric air is actually sorry, I just need to get this out of here. Okay, so I think my mouse is stuck over here. Never mind. So that atmospheric air is attached to the surface of the Earth. So the whole atmosphere is attached to the surface of the Earth. And if you look at the Earth diameter, it's 12,000 kilometers to give you a scale of things, while the atmosphere thickness from where you're sitting now to the outer space, to the edge of outer space, is only 100 kilometers. So it's a very short distance. You can, or horizontally, you can drive in maybe an hour. But the ratio of those is 1/1,000. And to give you an idea, so here is the atmosphere, the air on, if you gather all the air in the atmosphere, it's going to fill this much volume compared to the volume of the Earth. And here's another analogy or example to show you. Imagine that this is a this is a basketball, and it's a wet basketball, and that film is 0.2 millimeters, so that's 2 hair widths above the surface of the ball. So it's sometimes it can be hard to perceive, but that's the ratio. That's how thick the atmospheric air relative to the size of the Earth. So it's really a very, very tiny thin layer where we live, and it sticks to it very well. I don't know if you have watched or looked at the news recently about the moon. You know, there were new discoveries regarding the moon. Some part of the moon is rusting, and the reason is some of the oxygen in our atmosphere, and the part of the moon that's rusting is the one that's facing the Earth. And the reason that people or scientists believe this is occurring is because oxygen and some of the atmospheric air is just escaping, is being ejected from the surface of the Earth due to various reasons and hitting the surface of the moon. And but that's too much. We digress too much, but it gives you an idea of the thickness of the atmosphere. Okay, so that's one implication, is you can't take a helicopter up and let the Earth rotate. However, people like Elon Musk, and there's actually a new company that is coming up soon. They want to implement this type of idea, but not a helicopter wouldn't work, but actually a spaceship. You'll just travel up, get to orbit. So if you want to go fast, let's say you want to get from Beirut to Australia in 20 minutes or 30 minutes, then maybe not, maybe in an hour and a half, that's what you do. You just go out to the outer atmosphere, get your angle right, and then re-enter the atmosphere and land in Melbourne or in Sydney from Beirut. So this is the next age technology for traveling really fast instead of traveling in this very thick atmosphere of air. But that's beyond our course. The other implication is the tailwind and headwind. If you look at your monitor when you're flying, you'll see that you have ground speed, but also you see that sometimes you get a tailwind or a headwind. In this particular case, you have a tailwind of 83 miles per hour, and that's really why you can go. Typically, this ground speed of 600 miles per hour is not typical. This is actually above the average range of speeds that aircraft fly at. But these passengers have been lucky because they've had a wind at their tail. So the wind is at their tail, it's pushing them. Just because the aircraft is sitting in the wind, you're really getting this free 83 mile per hour speed. On the way back, however, an aircraft traveling in the opposite direction is actually unlucky. So it's not going to travel at 593. It's actually going to travel 510. So 593 minus 83, that's 510. Minus 83, so minus double this number. So it's going to only travel at 450, 430, 440, whatever, you do the math, ground speed. So imagine you're going 450 compared to 600, that's a 50% or 40% difference in velocity, which is huge. And instead of getting there in, I don't know, 6 hours, in 4 hours, you're going to get there in 6 hours. So you can see how much a difference that can make. And this is why it takes you different time heading east and heading west. So when you head east, it actually takes you less than heading west. And the reason is there is this jet stream that heads from west to east. So if you're moving in the eastern direction, you can ride in this stream and you gain this 83 miles per hour. But you would be unlucky if you're coming back on that particular path. You try to avoid it. It's not fixed in space, but on average, it's there. And there has been a record set this year. Not sure, I think it could be London, New York in 5 hours, less than 5 hours. Typically it takes 7. And that's the reason, is they were really lucky. Going New York to London, I think somewhere from America to Europe, going in under 5 hours, a trip that typically takes 6-7 hours. So that was a record. That's one implication. Another implication so it's tailwind and headwind. So let's look at tailwind and headwind, and let's see, am I still mic'd? I think I'm still mic'd. Let's look at tailwind and headwind. So here's an aircraft trying to land in headwind. So let's see so what I would like you to notice is the ground speed once this airplane touches down, when it's landing in headwind. So play. Okay. Okay, so it seems that the video, anyways, that's the link. I will post it so that you can watch it on your own. In fact, I'll just upload this updated version of the video. But you see, it sort of stops as soon as it lands on the tarmac. It doesn't travel too far. But look at what happens so its ground speed is actually very slow when it's coming into a tailwind. But look at its ground speed when it's trying to land in a tailwind. So that's landing in a tailwind. So maybe this video doesn't give it its fair message, just because it's not playing in real time. It's just delayed. But it's going. This aircraft, when it landed in tailwind, it took almost the whole runway to stop, while the previous airplane just landed. Just once it landed, it only took a very short period or range of the runway, a very small part of it to land. And the reason is because the ground speeds in both of them. So I'd like you to pay attention here as to why this is happening and why we make this observation. Primarily because in one case, the ground speed, the previous case, the ground speed is very small. In this case, the ground speed is very high. And what did we say about aerodynamic lift and force generation? We said it's the relative velocity that's really important to be able to generate enough lift. So you don't really want to crash your aircraft down really fast. You want to have it controlled. So for you to have it controlled, you really need to have both of them to have the same relative speed, the U infinity, the speed by an observer sitting on the airplane sees the wind coming at towards the airplane. So if we agree on this, let's say one of the airplanes flies into a headwind of 50 kilometers per hour and one flies into a tailwind of 50 kilometers per hour, just for our math. And both of them must have a relative speed of 300 kilometers per hour. So if you look at, so what should the ground speed be in the first case of headwind? So you see the airplane is moving into a headwind of 50 kilometers per hour. So if we agreed that for us to have good control of the airplane, we have to maintain the design speed, which is the relative speed. And it's the speed of the wind seen by an observer sitting on the airplane. So we're using the IJK vector notation. So plus I is a unit vector going to the right, and minus I is a unit vector going to the left. So the relative velocity of the wind is minus 300 I. So the relative wind is minus 300 or 300 going to the left, while the atmospheric air, just as you can see from the figure, because it's a headwind, is minus 50 going to, or 50 going to the left, towards the left. So what should the ground speed be in this case? For that to happen, minus 300 should be minus 50 minus 250. So your ground speed in a headwind should be 250 kilometers per hour. And now if you look at a tailwind situations, what we maintain, so now we flip this, instead of headwind, it's tailwind, but we still should maintain the relative speed so that we have the same amount of lift, the design lift speed. And so you stick in the 300 kilometers per hour is the relative wind speed that an observer sitting on the ground sees, sitting on the airplane, I'm sorry, sees. And then now you have a tailwind, so it's actually moving to the right. So it's plus 50 I. So for that to happen, you need your V ground to be to get a minus 300. So you can go up to minus 350, or plus 350, because there's a minus sign here. So in the previous case, we were going at 250 kilometers per hour. That is ground speed. That's the distance that will take you from point A to point B. While in the tailwind, you were actually going at a ground speed of 350 kilometers per hour. So in the first case, you touch the ground at this speed. Once you're at the ground, this is the speed that you're moving at, because you're now sitting on the ground. And in the tailwind case, you landed at this speed. and you had to break down to 0. In the first case, you had to break down from 250 to 0, while in the second case, in the tailwind case, you had to break from 350 to 0. And that's why it is significant, and it's a pilot has to be very careful. In both cases, they have to be very careful. They have to account for both cases. And sometimes if the wind is erratic and it's hard to manage, you'll just send them off. They can't land in that particular airport. You send them to somewhere else, an hour or 2 hours away, because they can't land there. Okay, so let me stop here and ask if there are any questions. Let me see, you can't chat. Let me just get back to the chat. Well, I do hope you can hear me.
Yes, we can hear you.
Yes. Options. Chat.
That's a small question.
Are you there? Okay,
I have a small question.
So you can see the chat. No, it's managed log. Okay, so let me just try something else here. No calling. Are you there? Yes. No. Questions? Can you guys see the poll?
No.
How about now?
Yes. Yeah.
Okay, you can see it. Great. Okay, someone has a question. So if you have a question, please speak up, unmute yourself and speak up before we move on.
Yeah, so I have a small question.
Ram, you have a question? You're muted. Yeah. I can't hear you. Actually, I apologize. I had my speaker muted. Forgive me.
So can you hear me now?
Yes, I can hear you. My apologies. This is a great lecture, but yeah, go ahead.
Okay, so a small question. If you're considering tailwind, basically we get so in order to maintain the 300 relative velocity, doesn't it mean that the airplane would have to use more fuel in order to maintain that relative velocity with respect to the air, which is itself 50 kilometers per hour?
Actually, it's the other way. It's both airplanes. They're both. So let's take this example that you just mentioned. Both of them are going at the 300 relative velocity, whether tailwind or headwind. Yeah, is that the question? So the answer is both of them are going to use the same amount of fuel, as long as your relative velocity is the same. Why? So let's just let me close the call for Rami. Can you hear me? Can you get my answer?
No, basically I had the system lag a little bit, so I didn't hear what you said.
That's okay.
You could repeat.
Yes, I will repeat. Let me just close the poll for a sec. Okay, calling. Close call. Okay, never mind. It's so the answer is in both cases the air, whether in headwind. Let's go back to this slot. Oops. No, we don't want this. I want this slide. In both cases, whether you're in tailwind or in headwind, in both cases you're going at a relative velocity of 300 kilometers per hour. So your mass fluxes and energy fluxes are actually the same. So you're actually going to use the same amount of fuel in both cases. But in the tailwind case, you're going to get there much faster. You're going to get this. You're going to spend that amount of fuel for only 4 hours, but in the headwind, you're going to spend it the same amount of fuel rate for 6 hours. So you
win. Okay. So basically, it's like I'm in the air, whether the air is traveling at a given speed or not. All I have to do is maintain that 300 kilometers per hour, and the fuel used is actually considered with respect to the atmosphere that's traveling at that speed. So regardless if it's tailwind or headwind, we actually use the same amount of fuel, right, to achieve this power.
That's right, and primarily because of those two equations that we have here. Because in both cases you have the same. In both cases you have the same relative velocity. And that relative velocity is what decides the mass flux of air that goes into your engine. So here we're assuming it's the two exact same aircraft models flying at the same time, same weight, everything, but they're going in opposite directions in that jet stream. So both of them are going to spend the same amount of fuel per hour. But one is going to spend it for 6 hours and one is going to spend it for 4 hours.
Yeah. Okay.
Yeah.
Thank you.
Yep, you're welcome. So, yes, please.
When we were talking about tailwind, isn't it coming in the same direction as the airplane is going?
Yes, the tailwind. So an observer sitting on the ground. So here is an observer sitting on the ground. They will see that, yes, the wind. So let's see exactly this picture. The wind is going to the right, and the airplane is going to the right. Yes. And the
relative wind speed as long as it's in the same direction as the airplane.
Because right, so that's what's okay. So here's your V ground is 350, right? To the right. So 350i, and that is 50i, and both of them are positive. But when you subtract 50i minus, because it's the VA minus VG. So it is because someone sitting on the airplane will, okay, let me just back up one step, explain this from the beginning. An observer on the ground will see that the atmospheric air is moving to the right at 50 kilometers per hour, and the airplane moving to the right at 350 kilometers per hour. But the pitot tube here will see that the wind is coming towards it at minus 350. So the wind is going to the right. So that's the V relative, if that makes sense, at minus 300.
So it's the speed of the air relative to the airplane, not vice versa.
So yes, the speed of the air relative to the airplane. Because this is a very basic concept.
So in all cases.
Please go ahead.
I want to say in all cases we'll consider it as a negative
Sulaiman, I think
because it's relative to A. not to.
You are right. Yes, you're right.
Right?
Yes.
Okay.
This is a very important concept. It's going to come later on. And in fact, what happens if the wind is coming perpendicular to, so let's say in this case, the wind is going to the right, right? Sorry, the airplane is traveling to the right, but the wind is going into the page. Is there going to be a relative velocity? Of course there will be, because it's the vector subtraction. So when you subtract, that's the wind, that's the airplane, that minus that. So it's going to be, so minus that, it's going to be this way. So you'll see that the wind, and that's why if you're traveling into a side wind, so that's a side wind, and that's your travel direction, your actual relative velocity is going to be in this is where you'll be traveling, because the wind will have you drift with it, and you have to correct for that. So somehow you have to keep turning right if you want to go straight. Yes, Jed, did you need to annotate, or this was by mistake?
Sorry, sir, I did not do it on purpose. Sorry.
That's okay. But please, if you need to write something, let me know. I'll approve you. Is this making sense?
Okay, thank you.
Okay. Any other questions? Just please unmute yourself and speak up. So let's just move on if there are no questions. And so now as we were saying at the beginning of the lecture, there is the kinematics and then there's the aerodynamics. Once we understand the kinematics and we can describe the motion, the position, the velocity, the acceleration, then we can take the acceleration, stick it into Newton's second law. Force times acceleration, or mass times acceleration gives me force. Then I can get those aerodynamic forces. But let's stick with the kinematics because we're still talking about it. So now imagine this is your airplane moving in this travel direction. So this is V, or the motion direction. It's moving in the X direction. So that's the forward travel speed. So the airplane has three linear motions. The forward direction travel, it can go up and down. That's when it lands and takes off. It moves in the Z direction. It gains altitude or loses altitude. And it can also turn sideways. So it can move in a plane forward towards the X, or turn left or right in the Y direction. So it yaws. And so these are the linear motions. There are actually also the rotational motions, because now you're an object moving in a three-dimensional space, but also you can have rotational motions. And the airplane rotating around the x-axis. So what happens if the airplane rotates around the x-axis? The wings will lift up. So the wing will do this or do this. So that's called the rolling motion. It rolls. So if this is my hand, that's the rolling, the airplane is traveling in this direction. It will be rolling left and right. So the travel direction is the x-axis, and the rolling motion is around the x-axis. And now the second angular motion is the yawing. So you're moving in the X, Z is up and down. So if I rotate in plane, left or right, that's the yawing motion. So I rotate around the Z axis. And if I rotate around the Y axis, then we call that the pitching motion. So you pitch when you want to take off or land. So these are the three descriptions, or the how we describe the motions: 3 linear and 3 rotational three rotational motions. So around the X, Y, and Z. Roll, pitch, and yaw. And if there's one thing I'd like you to remember in this course is you really need to know these motions. Because understanding these kinematics is necessary for us to understand the dynamics. And then we have the aerodynamic force generation. We have the lift that can point in the Z direction. That's the upward lift. We have side lift we've drawn it here, but it's generated by the rudder at the back, and as well, we have side lift, and then we have the drag force that drags your airplane. That's the friction, the air friction that you face opposite to your direction of motion, to your travel direction. So we will come and explain those in more detail in a second. So how do we control all these motions? So we said we have three linear motions and we have three rotational motions that we want to control.